So as I mentioned in the last lecture, the converse of theorem 2.2 that we did in the last lecture, which was the forward implication of the Arzelà Ascoli theorem, holds for a certain class of topological spaces called the locally compact Hausdorff spaces, and we will take this time to in this lecture to discuss a little bit about locally compact Hausdorff spaces. So let me give the definition first. So definition. So topological space X is called locally compact Hausdorff, LCH in short. If X is Hausdorff, of course, Hausdorff is part of the name, so we need it to be Hausdorff, and the part which is locally compact. So what is meant by locally compact? So given X in X, there exists a neighborhood U of X such that U closure is compact. So this means that every point has a neighborhood whose closure is compact. And this very simple property becomes extremely useful. And just as a remark, so locally compact Hausdorff spaces are extremely useful in topology and also in analysis. In particular, for areas like functional analysis and measure theory, locally compact Hausdorff spaces are extremely useful and basically indispensable for all kinds of results. So our interest in locally compact Hausdorff spaces is for the converse of the Arzelà Ascoli theorem, which we will see later. But first, let's prove a very basic and useful property of this kind of spaces, which is the regularity property. So all locally compact Hausdorff spaces are regular. So let's see a proof of this fact. So theorem. So locally compact Hausdorff spaces are regular. So a proof is given by putting a locally compact Hausdorff space within a compact Hausdorff space and as a subspace. So we know that compact Hausdorff spaces are regular, and all subspaces of regular spaces are also regular. So this will show that locally compact Hausdorff spaces are regular. So let's see a proof for this fact. So let X be a locally compact Hausdorff space, and what we will do is we will show that there exists a compact Hausdorff space let me call it X plus, such that X is a subset of X plus and is an open and dense subset. So not just a subspace, it is an open dense set. Okay, so what is this compact Hausdorff space X plus? So for this we use a technique called adding a point at infinity. So adding a point at infinity. So what does this mean? So we consider an extra point which we denote as P, but with the symbol infinity. This has nothing to do with the infinity of real numbers, but we just use it as a symbol. So just remember that we are using this symbol infinity, but it has nothing to do with the infinity of the extended real numbers, for example. So so what we do is we take the union, which we define as x plus. So as a set, x plus is just the union of x and this point at infinity. So this is called point at infinity. So x plus as a set is x union this point at infinity, and we take the following topology on x plus. So topologize x plus as follows. So the topology on x plus is by definition the topology on x, okay, which is the locally compact Hausdorff space we started out with, and we take the union with the sets of the form k complement union infinity, where k is a compact subset of x. So these kinds of sets are called neighborhoods of infinity, because it contains the point at infinity, and this kind of set is open. So this is why it's called a neighborhood of infinity. And I leave it to you to check that this tau x plus is indeed a topology. So as an exercise, check that tau x plus is a topology on x plus, and with this topology x plus is Hausdorff. Okay, so this is not very difficult to show. Using the fact that x is Hausdorff, you can also show that x plus is Hausdorff. Okay. Okay, so with this topology you have a space x plus which is Hausdorff, and I now claim that x plus is compact. So claim that x plus is a compact space with respect to the topology tau x plus. So why is this compact? So let u alpha in some set x be an open cover of x plus. So this open cover has two kinds of open sets, one that contains infinity and one that does not. So suppose we choose an open set u naught, or let me call it u infinity, which is a neighborhood of infinity. So u infinity containing the point at infinity p, and u infinity belongs to this open cover. So let me call this collection of open sets u alpha as A. So u infinity belongs to A, so it's one of these u alphas. So so it contains the point at infinity. Now u infinity must be of the form k complement union infinity. So notice, let me go back for a while. So in the first part where we have the topology on x, none of the open sets in x will contain the point at infinity, right? So only these neighborhoods of infinity contain the point at infinity. So u infinity must be of this form. It's k complement union infinity. And now cover k by finitely many u alphas from A. So say K is a subset of equal to 1 to n u alpha I, and then this implies that x plus is covered by the union u alpha I equal to 1 to n, and then union this set u infinity, because this covers k infinity, k complement union infinity, and this covers k. So both k and k complement as well as the point in infinity are covered. So this implies that x plus is compact. And to show that it is open and dense, so claim is also that x is open and dense in x plus. So open is easy, so x is open trivially, since tau x is a subset of tau x plus. So any open set in x is open in x plus, and x itself is open in x, so it is open in x plus. So to prove that it is dense, so we have to show that x closure is the whole set x plus, which is nothing but x union the point at infinity. So you only have to consider a neighborhood of a point of infinity, and to show that it intersects x, and then x closure will be x plus. So choose a neighborhood of infinity, say v infinity. So v infinity is open in x plus, so and contains the point at infinity. So infinity is contained in v infinity, and v infinity belongs to tau x plus. So it's an open subset of x plus in the topology tau x plus, and this means that v infinity is also of the form k complement union infinity for some compact set K. And now this means that there are points in v infinity which intersect x. So this means that v infinity intersection with x is non-empty, and this means that x closure is equal to x plus, because we only have to consider this extra point infinity, and we show that it is in the closure of x, and this means that x closure is equal to x plus. So this means that x is dense. X is dense. So with this we have the immediate corollaries. So the first one is that locally compact Hausdorff space is regular, because it is a subspace of a regular space. It can be seen as a subspace of a regular space, so it is also regular. The second one is that a locally compact Hausdorff space is Baire. Okay, so we have seen that open subspaces of Baire spaces are Baire, so locally compact Hausdorff space is Baire. So the first one, so let me just quickly write one lines for each. So this is because since x is a subset of x plus, and x plus is regular, and subspaces of regular spaces are regular. Spaces are regular. By the way, this by our construction, the subspace topology on X from the topology X plus on X plus is the same as the topology on X. Okay, so this you can check easily, because we defined the topology on X plus like that. So the subspace of regular spaces are regular, and so X is regular. The second one is that open subspaces of Baire spaces are Baire. So X is an open set in X plus, open set, and X plus is Baire. So because this is a compact Hausdorff space, as a compact Hausdorff space by the Baire category theorem, it is a Baire space, and X lies as an open subspace of a Baire space, so it is Baire. So these two corollaries give very nice properties, show that locally compact Hausdorff spaces enjoy very nice properties. And now let's prove a lemma which will be used in the proof of the Arzelà Ascoli theorem for locally compact Hausdorff spaces. So here is the lemma that we need, and this is about a joint continuity of the evaluation maps. So I will explain what this means. So for this we consider X to be a locally compact Hausdorff space, Y a metric space, and we consider the so-called evaluation maps. So what are these evaluation maps? So we denote it as EV, and this domain of this map EV is the product space X, Cartesian product with the space of continuous functions from X to Y, and the domain and the range of the map EV is just Y, and it is defined using the equation EVXF is equal to f of X. So here X belongs to X and f belongs to the space of continuous functions from X to Y. So we are just evaluating the function f at the point X, which is why this map is called the evaluation map. So the claim is that this map is continuous when the space of continuous functions has the topology of compact convergence. So let's try to show this. So proof. So let X comma f belong to the domain of this evaluation map, which is X Cartesian product with CXY, and let Y be the evaluation of X and f, which is nothing but f of X, right? So this belongs to Y. And now let V be a neighborhood of Y in Y. So we want to show that there exists an open set in X cross CXY. So now this one has the topology of compact convergence, and this is a locally compact Hausdorff space, and the product is of course given the product topology. Okay, so here we have to be careful what topologies we are choosing. So the open set is in the product topology, where X is the X is given the topology under which it is locally compact and Hausdorff, and CXY is given the topology of compact convergence. And we have to show that this evaluation map is continuous. So we want to show that there exists an open set in this product space, say U, such that it contains, first of all, X comma f is contained inside U, and the evaluation of U lies inside V. So this is the local formulation of continuity, local formulation of continuity of a function, which we did in one of the earlier lectures about continuity. And so we have to find an open neighborhood around the point xf such that the evaluation of this open neighborhood lies inside V. So for this, choose, first of all, note that Y is a metric space. So choose epsilon greater than 0 such that BD Y epsilon lies inside V. So this is a basis set in the metric topology, and so there exists an epsilon greater than 0 such that this is true. Now consider an open neighborhood, say U1 of X, such that U1 closure is compact. So this is by the locally compact Hausdorff property of X. And now consider the open set. Actually, it's an open neighborhood of the point X. So let me call this U2, which is U1 intersection with F inverse of the metric ball around Y with radius epsilon by 2. So since F is continuous and this is open, F is continuous, so this is open, and of course this is, we have chosen it to be open, and so Y2 is open in X, and U2 closure, this is the closure of the intersection Y epsilon by 2 for closure. This is a subset of the closure of U1, which is compact. This is compact, and therefore U2 closure being a closed subset of a compact set, this implies that U2 closure is compact. So now take the basis element in the topology of compact convergence, which is given by BCF epsilon epsilon by 2, where C is equal to the closure of U2. So this is our basis element containing F in the topology of compact convergence in CXY. So in fact this should be BCF epsilon by 2 intersection CXY. Okay, so these are only continuous functions. So now we can take, let U be the open set U2 Cartesian product with BCF epsilon by 2, and I claim that the evaluation of U is a subset of V. Okay, so in other words, if X prime G belongs to U, which is by our definition U2 Cartesian product with BCF epsilon by 2, where C is U2 closure, then this implies that the evaluation of X prime G belongs to V, and this is the same as saying that Gx prime belongs to V. So what we have to show is that given X prime G in U, then the evaluation of G at X prime belongs to V. So to prove this, we use the facts that we have. So first of all, we have that since X prime belongs to U2 and G belongs to BC F epsilon by 2, so we have that the supremum of X prime in actually we can take X double prime here just to distinguish it from the point X prime. So X double prime in C, which is U2 closure, the distance between Fx double prime Gx double prime is less than epsilon by 2. And now since we have x prime is in U2, which is subset of U2 closure. This means that the df of x prime gx prime is less than epsilon by 2. So this is one of the inequalities that we need. On the other hand, since x prime belongs to U2, which is a subset of f inverse of BD y epsilon by 2. So this was a subset of f inverse V, for example, and this means that f of x prime belongs to BD y epsilon by 2, and this is the same as saying that the distance between fx prime and y, which is f of x, is less than epsilon by 2. Okay, so this is y out. Now so this is again one of the inequalities that we need. So from star and star point 1, so from star and star point 1, we have that the distance between g of x prime and f of x, this is by the triangle inequality less than or equal to g of x prime g of x, f of x prime here, plus the distance between f of x prime and f of x, right? And we just go back and see. So the first one is by star less than epsilon by 2, and this is from star point 1, this is less than also epsilon by 2, and so the sum is less than epsilon, which means that g of x prime belongs to the metric ball around f of x with radius epsilon, which is nothing but BD y epsilon, and by our choice of epsilon, this was a subset of V. So we have shown that g of x prime belongs to V, and this is what we wanted to show. So this means that the evaluation map is continuous. So this is the very nice lemma that we want to use for our proof of the converse of the Arzelà Ascoli theorem, which we will take up in the next lecture.